We want to find the volume of the solid bounded by the two paraboloids shown here. Let's first look at this graphically. So here we see the graph of the two paraboloids. Again, our goal is to find the volume bounded by these two paraboloids, which would be the volume of this solid here. We're actually going to do this using a double integral in polar form. One reason for doing this is, if we take a look at the intersection of these two paraboloids by looking down on the xy plane here, notice how it's a circular region in the xy plane, which will be our region of integration. And therefore, it's going to be easier to evaluate this using a double integral in polar form. So going back to our work, looking at this double integral in polar form, because we're trying to find the volume bounded by two functions, f of r comma theta is actually going to be the top function minus the bottom function once we find the equations in polar form. Let's first do that. Actually, before we do that, let's identify which of these functions is the top function and which is the bottom. Notice we evaluate these at the point 0, comma 0. Here we'd have z equals 7, and here we'd have z equals negative 6, which means this is the top function, and this would be the bottom function. So let's first write z in polar form. So we can call this f of x comma y is equal to 7. Now let's factor out the common factor of 2 here. So we'll have minus 2 times the quantity x squared plus y squared. And we'll call the bottom function g of x comma y, which we'll write as negative 6. Let's also factor out the 3. So we have plus 3 times the quantity x squared plus y squared. Now because x squared plus y squared is equal to r squared, we can now easily write these in polar form. F of r comma theta would be equal to 7 minus 2r squared, and g of r comma theta would be equal to negative 6 plus 3r squared. Now we need to find the intersection of these two paraboloids, which will help us determine our region of integration. So we'll solve this as a system of equations. So we'll set 7 minus 2r squared equal to negative 6 plus 3r squared. Let's add 2r squared to both sides, as well as add 6 to both sides. So that would give us 13 equals 5r squared. Divide both sides by 5. So we have r squared is equal to 13/5. And now we'll take the square root of both sides of the equation. So algebraically, we do get r equals plus or minus the square root of 13/5. But either equation is going to give us a circle in the xy plane with the radius of the square root of 13/5. So we'll just use r equals the square root of 13/5, which I've actually already graphed here on the xy coordinate plane. So this is the graph of r equals the square root of 13/5. But because we're looking for the volume bounded by these two paraboloids, the region of integration is going to be the circle as well as the area inside the circle. So this is our region of integration. And now we have all the information we need in order to set up our double integral in polar form that will give us the volume bounded by these two paraboloids. The volume is going to be equal to the double integral of, again, f of r comma theta is actually going to be f of r comma theta minus g of r comma theta. So we're going to have the quantity 7 minus 2r squared minus the quantity negative 6 plus 3r squared. Now remember, in polar form, we do have an extra factor of r here, so now we have r dr d theta. And now we need to find the limits of integration for r and theta that would trace out this area in the xy plane. Well, we know r would be from 0 all the way to the square root of 13/5. So limits of integration for r are from 0 to the square root of 13/5. And then to trace out the area, we have to rotate one full revolution. So we have from 0 to 2 pi radians, which would be the limits of integration for theta. Let's go ahead and simplify the integrand function. We're going to have 7 minus negative 6, that's 13. And then negative 2r squared minus 3r squared, that's going to be minus 5r squared. And then we still have r d theta. Now let's go and distribute here and write this as 13r minus 5r cubed. So again, the integrated function would be 13r minus 5r cubed. And now we integrate with respect to r. So the antiderivative would be 13 times r squared divided by 2, or 13 halves r squared, minus 5 times r to the fourth divided by 4, or minus 5/4 r to the fourth. So when r is equal to the square root of 13/5, we'd have 13 halves times, well, the square root of 13/5 squared would just be 13/5, minus 5/4 times the square root of 13/5 to the fourth would be 13/5 squared. Then, of course, when r is 0, these will both be 0. Now we need to simplify this expression here. Here we have 169 tenths. And then we have minus 5/4 times 13/5 squared is going to be 5/4 times 169 tenths. It comes out to 169 twentieths. And then this difference comes out to 169 twentieths. And now we integrate this back to theta, so we have 169 20ths theta. And the limits of integration are from 0 to 2 pi. So 169 20ths times, when theta is 2 pi, we have 2 pi. When theta is 0, we have 0. So this just simplifies to 169 20ths times 2 pi over 1, common factor of 2. So the exact value of the volume bounded by the two paraboloids is 169 pi divided by 10. So again, we just found the volume bounded by these two paraboloids using a double integral in polar form. I hope you found this helpful.